Hey everyone, welcome back to Trigonometry. This is going to be lecture 4 of the course. And in this section we are going to once again extend our definition of the trig functions, this time to the most general sense where we are able to find the value of the trigonometric functions for any angle. Okay, so let's go ahead and jump into it. We'll call this section 1.4. Trig functions of any angle. Okay, and so let's kind of jump back to the equilateral triangle from the previous section, right? So remember we had a triangle that was equilateral here, and maybe this was 60 degrees, 60 degrees, 60 degrees, and again 2, 2, and 2. And from that, if you'll recall, we split it in half, dropped a vertical, and got this right triangle, where we have the 60-degree angle and a 30-degree angle. And in that section, we discovered that the sides were 1 and 2, obviously, and that this one here is the square root of 3. Okay, now let's go ahead and take this and insert it into a coordinate system here. So I'm going to put in my y-axis and my x-axis, and I'm going to draw this on here like so. And so I've got a hypotenuse of 2 here that represents the length of this ray, and then I've got 1 down here, and then I've got square root of 3 up here, right? And so the way we think about it when it's in the coordinate system like this is that this is the length 1 and this is the length square root of 3, right? And so this point up here you can think of as xy and being equal to 1 comma square root of 3. Okay, and so we can imagine this triangle situated in the rectangular coordinate system like this with the 60-degree angle located at the origin, right? And so this is going to prompt a slight generalization of the previous definition of the 6 functions. So let's write that out. So the definition, let's let theta be any angle in standard position. Okay, any angle in standard position, and let P equals xy be a point on the terminal side of theta. Okay, so any point on the terminal side of theta, right? So this is the angle theta here. This ray here represents the terminal side of that angle, and this point xy is some point on there. Okay. Then if and we're gonna, let's see, I'll write it here. If r equals the square root of x squared plus y squared, this is going to be the distance from the origin up to the point xy. And I'll put that in parentheses here. This is the distance from 0, 0 to xy. Okay, so if that's what r is equal to, then the 6 trig functions are, okay, and so this is going to be the sine of theta is equal to y over r. The cosine of theta is equal to x over r. The tangent of theta is equal to y over x. Of course, this is where x is not equal to 0. Okay, and then the other 3 are the reverse, right? The cosecant of theta is r over y. The secant of theta is r over x. And the cotangent of theta is x over y, of course, where y is non-zero. Okay, and we can see that this is really just a generalization of our first definition, right? So this is a generalization of our unit circle definition. Right, in the unit circle definition, we had sine of theta equals just y. Right, now remember what we had there was, we had a point on the unit circle. This is xy, right? And we said that this is the length y. And then because it's a unit circle, this was always 1, wasn't it? Right? But really what's going on here is that really it's y over 1, right? And so if we just extend the unit circle definition a little bit, then we can see how we can get from a sine of theta equaling y to a sine of theta equaling y over r. In this case, r doesn't have to be 1. It can be anything, right? The key here, the key is figuring out what r is, right? The key is figuring out what r is, and so r is equal to the square root of x squared plus y squared. That's just basically a straight application of the Pythagorean theorem, right? So remember, this is a right triangle here. Here's your x side, there's your y side, and the hypotenuse is 1, right? So, but if the hypotenuse is unknown, right, and we're not talking about a unit circle, then I can figure out what this length is by using the 2 legs inside the Pythagorean theorem. Okay, let's do an example using this definition. I think it's very easy to figure out how this works through a couple of examples. Okay, so let's do an example here. Let's let p equals -3, -5 be a point on the terminal side of theta, right? And we're just going to assume that theta is in standard position, right? Okay. Well, I won't write that. Well, I'll write it. Assume theta is in standard position. Right now, no, most of the time it won't say that, but just know that if it doesn't say that, that's the assumption you should make, is that it is in standard position. Let's find sine of theta, cos theta, and tangent of theta. Right? If we can find these 3, we can find the others. So let's see what this looks like. So let's draw in our coordinate system, right? And so p is over here. So 1, 2, 3, 1, 2, 3, 4, 5. And so p is actually right here. And so you can think of it as there's a ray like that, and theta is this whole angle. Okay, this is your x-axis, of course, and your y-axis. Okay, and so we need to know how long this ray is, right? And really the way this would work is you'd be really kind of trying to think about it as a triangle like that. But how long is that ray? Well, r is equal to the square root of x squared plus y squared. We're given x and y, and so we can figure this out pretty easily. -3 squared plus -5 squared. And so that's equal to 9 plus 25, which turns out is 34. Square root of 34. Okay, so this length is square root of 34. Not quite 6. Okay. And so, easily, we can see that the sine of theta was defined as y over r. And so y over r is -5 over the square root of 34. And so that we can rationalize that. -5 times the square root of 34 over 34. What's the cosine of theta? It's equal to x over r, and so it's -3 over the square root of 34. And so -3 square root of 34 over 34. Okay, and then the tangent of theta is equal to y over x. And so it is -5 over -3, and so it's 5/3. Okay, and so there we go. All right, so given a point, arbitrary point in the plane, we can find the angle that is implied by that point, if you assume the angle is in standard position. and that the point is on on a ray that's on the terminal side. Okay. Okay, perfect. Next, let's talk about positiveness and negativeness of trig functions. Okay, and so the positiveness and the negativeness of trig functions. So this can be reliably determined by basically the quadrant in which the terminal side of the angle falls. And so let's think about this with an example here. Right, so if I've got my xy plane here, I've got my xy plane, and let's think about cosine and sine as an ordered pair, right? We know cosine represents the x distance, sine can represent the y distance. So in quadrant 1 over here, I'd be moving this direction and this direction, right, to be up in here. And so over here, cosine is positive and sine is also positive, right? And tangent is positive, okay? Right, because tangent is the ratio of those two. What happens in quadrant 2? Well, over here, I've got my cosine is negative, isn't it? Right? Think of cosine as the x direction, and that's going to be negative here, right? Because I'm going this way on the x-axis. And y, or sine, is still positive. Right? So over here, I've got a negative and a positive. Okay. What about down in quadrant 3? Well, here they're both negative, aren't they? Right? Negative on the x-axis, negative on the y-axis. And then in quadrant 4, I've got a positive cosine and a negative sine, don't I? So the thing to keep in mind here is that because r is always positive, right? R is always positive. The value of the sine will be either plus positive or minus negative, based solely on the values of x and y. Let me write that down. Right, just keep this in mind, because r is greater than 0. Because r is greater than 0, the value of the trig function will be positive or negative based purely, solely on the x or y value, right? So the r doesn't matter. I mean, r is always positive, right? So if x is positive, then you're going to automatically get a positive cosine. If x is negative, you're going to automatically get a negative cosine. Okay, and we can kind of summarize this. So if we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4, and we just put sine, cos, tan, and then we'll put these others on here as well: cosecant, secant, and cotangent. And let's go ahead and let's just write these out and see what kind of patterns we can see. Okay, and so we just did the sine and cosine. So sine is positive here and positive here, and it's negative in these other two places. So positive, positive, negative, negative. Cosine is positive in the first quadrant, and then negative in the second, and then positive in the third, and negative in the fourth. So it goes positive, negative, positive, negative. Now, thinking about the cosecant, which is, you can think that's a reciprocal of sine. Now, the reciprocal operation doesn't change the sign, right? So it's going to be the same: positive, positive, negative, negative. And so the secant will also mirror cosine. So it'll be positive, negative, positive, negative. Okay, now what about the tangent? The tangent, now remember, the tangent is the ratio of sine and cosine. So the only time tangent will be positive is if both of these are positive or both of them are negative. So you're going to have a positive tangent here, positive tangent there, and these others will be negative, right? A positive divided by a negative, negative divided by a positive. They're both going to generate negatives. The cotangent is going to be exactly the same. It's just the reciprocal of the tangent. So you'll have positive, negative, negative, positive. Now, I don't expect people will necessarily rely on this this table, but it's just something to point out, right? That structurally, the sign of the trig functions is totally predictable based on what quadrant the terminal side of the angle lies in. Okay, and so it's just interesting to think about that. And I wouldn't expect you to memorize this, but just keep this in mind that the sign is generated by basically the quadrants, generated by the x and y values. Okay, very good. Okay, and so what we want to do next is we want to talk about, we want to introduce the idea of a reference angle. Okay, so reference angles are going to be a way to recast a kind of big and or confusing angle so that it's in it sort of as a simpler angle, as a simpler but equivalent angle. Not equivalent angle, but equivalent in from the vantage point of the trig functions. So let's start by defining it, and then we'll do a lot of examples and try to flush it out. So we're going to let theta be a non-acute angle. Yeah, non-acute angle. What does a non-acute angle mean? Just an angle that isn't acute, right? So remember, acute angles are angles, if you think about the xy plane, they would be angles in quadrant 1, right? These are acute. Technically, an acute angle is an angle that's less than 90 degrees. Okay, between 0 and 90 degrees. And so we're talking about non-acute angles. So we'll be talking about angles that are at least 90 degrees. Okay. Okay. All right, so that's kind of an aside. So let theta be a non-acute angle in standard position. Okay. We're going to let it be a non-acute angle in standard position that lies in a quadrant. Okay. All right, well, naturally that's going to happen, right? Its reference angle, that's what we're defining. Its reference angle. Okay, its reference angle is the positive acute angle it's the positive acute angle, we'll call it theta prime, formed by the terminal side of theta and the x-axis. Okay, so what the heck does this mean? So let theta be a non-acute angle in standard position that lies in some quadrant. Its reference angle is going to be the positive acute angle formed by the terminal side of theta and the x-axis. Now, I wouldn't expect from this definition that you would have any kind of conception of what this is. So let's take a look at some examples. Let's draw some examples, and I think the idea will come out. Let's say I've got a terminal side up here, right, and that this is theta. What's the reference angle for theta here? Okay, the reference angle, now what does it say? It's the positive acute angle formed by the terminal side, so that's the terminal side, and the x-axis. So the way you can think of it is you can drop a perpendicular onto the x-axis, right? This is the x-axis, and the angle that is formed that is formed inside that triangle, that is the reference angle. Right? So this is the reference angle. Right? And you can see that it's going to be a positive angle, and it's going to be less than 90 degrees. Okay, that's one example. What about this example? Let's say I've got my terminal side here. Excuse me, and this is my theta. Then what's my reference angle? Well, you can kind of think of this as dropping down here, and it's this guy. Right? So it's going to be the angle in the triangle that you get when you drop a perpendicular, or in this case, raise a perpendicular up to the x-axis. What about this guy? Let's say I've got something over here, right? And here's my theta. And so you can kind of think of the triangle as being here, and theta prime is going to be that angle, isn't it? Right? So we're just looking for an angle that the ray makes with the x-axis, essentially. Okay. An acute angle that the ray makes with an x-axis. Okay. Let's do some examples here. Let's find the reference angle. Find the reference angle, theta prime, for the following angles. Let's put a bunch of them on here. So A, will say theta equals 345 degrees. B, will say theta equals 5 pi over 6. For C, theta is equal to negative 135 degrees. D, we'll say theta equals 2.5 radians. Okay. Okay, let's start with A. Theta equals 345 degrees. Let's start with this one. So we don't need to know exactly what this angle looks like, but we just know that it's between 270 and 360. So it's somewhere down here, isn't it? Right, that's the angle 345 degrees. And so we can easily see what the reference angle needs to be. We're going to drop that perpendicular to the x-axis, and we know that this is our theta prime. All right, so how can we figure out what that is? Well, kind of the way to think about it here is that all the way around is 360, but we've gone 345, so the difference is the reference angle in this case. So theta prime in this case can be thought of as 360 degrees. That's a whole revolution minus the 345 degrees. And so we can see that that's 15 degrees. Right? So theta prime is 15 degrees in this case. Okay. All right. Let's do another one. What about B? Theta equals 5 pi over 6. What about that one? So theta equals 5 pi over 6. What does that look like? Again, I recommend drawing these until you're very comfortable with, 5 pi over 6 is over here somewhere. Right, so you got to think about breaking the upper half into 6 parts. So 1, 2, 3, 4, 5, 6. And so this is the 5th part. Okay, and so this would be theta equals 5 pi over 6. Now the reference angle, and if you're just looking at the picture, would be this part here. Right, it's going to be the angle formed by the terminal side of theta and the x-axis. Okay, and so what is that? How can we figure that out? Well, all the way to this side here would be pi, and we've gone 5 pi over 6, so I got to subtract that part off. Right, so that would be 6 pi minus 5 pi over 6, and so pi over 6. Okay, so pi over 6 is the reference angle for part B. Now what about part C? Here we said theta was equal to negative 135 degrees. So what does that look like? So this one, because it's negative, you have to be a little more careful, right? So basically we have to go clockwise 135 degrees. Well, that would be 90 degrees. So it's somewhere over here, isn't it? Negative 135 degrees. Okay. And so what is this difference here? Well, here you can kind of you can think of negative 100. This is going to be the reference angle, right? Obviously, I guess I should say that. Theta prime is this guy, right? This distance here. And so you can think of negative 180 degrees, right? And then I want to subtract off the negative 135. And so when I do that, I get negative 45 degrees, don't I? So negative 180 plus 135. So I get negative 45 degrees, but the key here, the thing to keep in mind is that the reference angle always is positive, so theta prime needs to be positive 45 degrees, right? So let me write that in here, but the reference angle so we would say theta prime is equal to 45 degrees. Okay, simple enough. And then what about this 2.5 business for the part B? Right, 2.5. Well, so when we say 2.5 radians, whenever pi is not in the radian angle, you have to think about it kind of logically. Now, if I were to draw this, right, and we think of the whole angle over here as pi, and so that would be 3.14159, etc. radians, right? So it's 3.14 all the way to here, and this would be half of that, so about 1.57 or so, right? And so 2.5 is somewhere in here, isn't it? I should put radians here just to make that clear, because we're not used to seeing those angles without the pi there. So 2.5 radians. And so the reference angle is going to be this part, right? And so what is that? Well, this is pi all the way to here, and that's 2.5, and so I could just do the subtraction, couldn't I? I could say something like this. It's pi minus 2.5. And that's going to be approximately 3.14 minus 2.5, and so it's approximately 0.64. Right, so the reference angle in this case is approximately 0.64. If you wanted to say it precisely, you'd say it's pi minus 2.5. That's a precise reference angle, but if you want to put it all as a real number like this, or as a decimal number, a single decimal number, you could write it as approximately 0.64. Okay, very good. All right, now so that's how we find reference angles. Now what's the usefulness of this? Okay. Well, we'll see in a second here. Let's do another example where we find a reference angle, one that's kind of a weird one. So let's find a reference angle. Find a reference angle for theta equals 8 pi over 3. Okay, so first, notice, note that 8 pi over 3 is greater than 2 pi, right? So what that basically means is we're going to go around the circle more than once, right? And so we can simplify this problem by identifying a coterminal angle less than 2 pi. So we can simplify this problem by finding a coterminal angle less than 2 pi, right? So coterminal angle, remember, were angles that had the same terminal side in standard position. Okay, and so if we can find some angle less than 2 pi, then the reference angle will be easier to identify. Okay, and so let's try to find a coterminal angle. So if I take 8 pi over 3 and I just subtract off 2 pi, what do I get? Well, I get 8 pi minus 6 pi all over 3, right? And that gives me 2 pi over 3. Okay. And so 2 pi over 3, right? So theta is whatever, 8 pi over 3 is now going to be, you can see that it's coterminal with 2 pi over 3. So it's coterminal with 2 pi over 3. Let me just make sure that we're clear on what that's doing, on what we're doing here. So the 8 pi over 3 basically goes like this. It starts here and it goes around once, and then it actually ends up over here somewhere. So this is 8 pi over 3. Now what we're saying is, look, that's kind of a goofy, tricky angle. So let's figure out an angle that's less than 2 pi, a coterminal angle. Right, and just kind of looking at the picture, you can see, well, really the only part that matters is this part. It's the part that extends from the x-axis up to this terminal side. And so really what we're looking at is, what we really care about is this part. And that happens to be the 2 pi over 3. Okay. And so once we've got it in this form, it's easy to think about what the what a reference angle would be. Right, you can just say, oh, look, it's this piece here, right? And so theta prime must just be the pi minus 2 pi over 3. So theta prime equals pi minus 2 pi over 3, which is, of course, pi over 3. Okay. So that's a good example, kind of using a really more unusual angle. Here's one more, just because this reference angle stuff can be a little tricky. Let's do one more example where the angle is really nutty. So let's find a reference angle for theta equals negative 13 pi over 6. Okay, and so again here you can clearly see 13 pi over 6 is going to be way more than 2 pi, right? So it's more than 4 pi in fact. So 4 pi would be 12 pi over 6. Oh, sorry, that'd be 2 pi. Yeah, 12 pi over 6. So let's subtract off, we want to subtract off 4 pi though because we want this to be positive. Well, let's see what happens here. So let's start with negative 13 pi over 6, and let's add to that 2 pi. Okay, when I add to it 2 pi, I get negative 13 pi plus 12 pi over 6, which is negative pi over 6. Now, it's still negative, right? But I mean, so we could figure this out, using the negative angle if we want to. And so actually, you could do it this way. You could also add another 2 pi if you wanted to. So you could go negative pi over 6 plus another 2 pi to get another coterminal angle. And you'd see that that's negative pi plus 12 pi over 6. And so you get 11 pi over 6, right? So these are the same. I mean, these are coterminal with one another. It's just a question of which one you prefer, right? So if you think about it like as a negative, then basically it's going to be down here, isn't it? Right? You can think of just moving 1 pi over 6 in the negative direction. Now, equivalently, you could think about it like this, and here you're moving 11 pi over 6. Okay, so it's really like whatever you're more comfortable with. They're both the same. You can think of it as going like that or as going negative. Right, but either way, the reference angle is going to be formed like so. If we drop the perpendicular onto the x-axis, implies a triangle, and the central angle is the reference angle. And so theta prime in this case could be found using 2 pi minus 11 pi over 6. And we know that that's going to be 12 pi minus 11 pi over 6, which is pi over 6, right? And we could kind of intuit that from this, right? So if this was negative pi over 6, and the reference angle would be pi over 6 positive, right? So theta prime is pi over 6. Okay. Okay. So those are some good examples of finding reference angles. Let's do a problem now that kind of shows the usefulness of this, right? So sometimes we'll be given an angle and asked to find a trig value for an angle. But we won't have, we will not have looked at that angle specifically. We won't have exact values for that angle. But it may be the case that we have exact values for a reference angle or a coterminal angle. Okay, so let's do an example where those come into play. All right, so find the exact value of tangent of 14 pi over 3. 14 pi over 3. Now notice that 14 pi over 3 is not an angle that we have an exact value for. But we could start by finding a coterminal angle less than 2 pi. So let's do that. Right, so 14 pi over 3, one way to think about this is to notice that this is like, the 14 over 3 is like 4 2/3. Okay, so 2 pi is a whole revolution. This is 4 2/3 pi, right? So that means we can subtract 4 pi from this. Okay, so 14 pi over 3 minus 4 pi will equal 14 pi minus 12 pi over 3. And so you get 2 pi over 3. Okay, and so 2 pi over 3 is coterminal with our given angle. So we'll say 14 pi over 3 is coterminal with 2 pi over 3. Okay, so let's draw it. As soon as you've got a reasonable coterminal angle, I recommend drawing it. So 2 pi over 3, that's the angle we were just looking at. It's somewhere like this. Okay, and so the reference angle would be this guy, which is pi over 3. Okay, so theta prime, the reference angle, is pi over 3. Now notice, we don't have an exact value for tangent of 14 pi over 3. Right? But we do actually have an exact value for tangent of 2 pi over 3 or tangent of pi over 3. Right? We do have exact values for that. Okay, and we can just look that up in our notes. We can see that the tangent of pi over 3 is equal to square root of 3. And that's also the same as the tangent for 2 pi over 3. Right, so kind of one of the things about reference angles and coterminal angles is that the trig functions are going to have the same value for all coterminal angles and for reference angles. Right, and so it's very frequently a good idea and helpful to reduce a goofy angle like 14 pi over 3 to either a coterminal angle, or even if the coterminal angle is goofy, to a reference angle that may be less goofy. Right, and so a lot of times you can take an angle that seems like we don't have a value for it, and you can reduce it to something that you do have a value for. Okay. Okay, let's do one more example kind of like this. Here's another example, similar. let's find the exact value of secant of negative 17 pi over 4. Okay, and so the secant, we definitely don't have an exact value for negative 17 pi over 4. But let's see if we can reduce this down to something that we do know. Okay, so if theta is equal to negative 17 pi over 4, then we could find a coterminal angle by adding 6 pi to this. A nice coterminal angle between 0 and 2 pi. I'll write that down. Then a coterminal angle between 0 and 2 pi can be found by adding 6 pi. You don't necessarily have to figure that out right away, but I mean, you can just see that 17 over 4 is, let's see, it's, what is it, 4? Yeah, so it's greater than 6 pi, right? It's greater than 6. So you can easily take the negative 17 pi over 4 and you can add 6 pi to it. And so when you do that, you get negative 17 pi plus what, 624 pi and over 4, and you get, so that's a negative, sorry. And so negative 17 plus 24 is 7, right? Yeah, 7 pi over 4. Right, just doing that arithmetic there. Okay, and so what does that look like? Right, so 7 pi over 4 is going to be, well, here's 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7. So it's down here. Okay. And we do have we have identified a value for 7 pi over 4, but let's think through the reference angle. This must be this guy, and that's just going to be pi over 4, which is kind of an easier one to think about. Pi over 4, we know, that's the 45 degrees, isn't it? Right, and so we're looking for the secant of negative 17 pi over 4. That's going to be equal to the secant of pi over 4. Right, and if you look through back into your notes, you'll find that this is equal to the square root of 2. Okay, you'll find that the secant of pi over 4 is equal to the square root of 2. Okay, very good. Okay, and so I think that's where I'm going to end this lecture. Again, this section, right, the goal here was to lay out a definition for trig functions that's the most general, which is kind of what we started with. And then we introduced the idea of reference angles. And in the next section, we'll get into graphs of trig functions. So we'll kind of shift gears a little bit, and we'll start talking about what the trig functions look like when they're graphed on an XY coordinate system. So, all right, until then, take care, and we'll talk to you all later.